right, so my name is Michele McColgan. I work for Siena College, a liberal arts college in upstate New York, and I'm a physics professor, department chair now, and I've run an informal STEM program for many years where I did an academic program during the year, and I also ran summer STEM camps. And personally, I also taught a lot of classes for homeschool groups like robotics teams and science Olympiad and science and math courses and activities. So it's close to my heart. So today I'm going to talk about the informal STEM program and my MARVLS apps that developed kind of from the transition from the Urban Scholars Program. But you can just see the picture here. Here, the top picture is a picture of like one of the starting meetings that we had during the day in our informal program. It was a program that's an out-of-school program for middle school students in upstate New York, and it started in 2003, and I added STEM content in 2009, and we finished due to COVID at the end in spring 2020. But the program was to increase participation of African American, Latino, and female students by maintaining their positive attitudes towards STEM through the middle school years. And it was funded by the local school district, high needs district, and Siena. And we accomplished this by having long-term, high-quality STEM experiences. So we had classes 14 Saturdays through the academic year that were all day on Saturday. We had supportive STEM role models as teachers and mentors that were paid. We also had education students that were mentors, so we had a lot of support in the program. We had a really positive program where we trained the mentors, and we also, one of our themes was things are challenging, but you have a lot of support. And then the program was free to students, and we had free lunch and free transportation. And that's where most of our funding went to pay for that. Here are some of our demographics. So we had in the district, so you can see we're comparing district to our program. So we had a little more females than we did males in the program. Our program was pretty representative of the low poverty and high poverty areas. So we had a lot more students from the high poverty areas. And then you can see the demographic makeup that we were pretty consistent. We had slightly more Black students than we had, white students or Latino students in the program. So our teachers and mentors as role models, you can just see some pictures here. There's a lot of adults in the room along with the kids. But we had STEM faculty leading. So we had a leader with experience in that topic. We had around 6 classes in the morning and 6 classes in the afternoon, and we tried to limit students to around 12 students. So there was a lot of support. We had pre-service education students, and we also had a lot of high school mentors with technical expertise. So they were really great at like helping us build our Minecraft worlds. So we had lots, like I said, since we had 6 classes in the morning and 6 classes in the afternoon, we had a lot of different classes that we offered, a lot of novelty and different things that we did. There were hands-on activities, there were computer activities. We had students with computers that were donated to us, and students took them apart, put them back together, went through this curriculum, took them home for keeps. We had a lot of physics in Minecraft. We had circuits, egg drops, mousetrap vehicles, coding, Scratch. We had App Inventor, Tailblazer. We had programming and Python, robotics, painting and cooking. So those painting and cooking classes were really to get the kids that were like, I don't really like science, but I want to go. And they have painting. And so we would get a lot of the kids to come that really weren't really interested in science, but they wanted to paint or cook. And then they were allowed to take that they could take that once, like in the morning or the afternoon. So in the other class, they'd have to pick a different class in the other part of the day. These were just a couple of examples. We had many, many physics and Minecraft worlds that we did. So you can see on the left, this was like a particle physics world that was created by a student that actually got a PhD, went on to get a PhD in particle physics at Purdue. The one on the bottom was some of our students were interested in like fission and fusion, and so they created chambers and little activities to go in there. And then the one on the top right, students used redstone to be able to make waves. So they had to make a wave and measure the amplitude, measure the period, things like that. So how did we recruit? I actually went in with sometimes some other students, and I went into 5th grade classrooms in participating schools. So I had a group of teachers that would always invite me back, and I would show them pictures of the kids from the year before doing things in our program. So the 5th grade teachers were like competing to try to get all the kids in their classes to participate. That was their goal, which was really nice. And we didn't pick, we asked teachers actually not to pick strong students. We just wanted anyone that was interested to come. So you'd think that we'd have way too many students, but we didn't, because we still had to get permission slips signed. We still had to get students, going to the buses and things like that. But we really worked with how many schools were we going to try to get as many students in those schools to come. Um, and so, yeah, you can see some pictures here. The kids were walking back from lunch. So the students were able to go around campus. We had classes in different buildings. We had lunch in a different building. Sometimes our like big meetings would be in a different building. So students were able to really understand what the college campus was like. And this is an example, the food was always a huge motivator for kids. And so we showed them, what does the cafeteria look like and what food were they eating and things like that. So they love the cafeteria. The program was for fifth graders to eighth grade students, and we sometimes would be able to keep some of our high school mentors, but they were here on campus 14 Saturdays for a total of 70 contact hours per year. 93% begin in fifth and sixth grade, and so 41% of the participants were fifth and sixth graders, and then we have 59% seventh to eighth graders. So that was amazing that we were keeping students in seventh and eighth grade, and 92% of our students participated for 2 years or more. And so of the groups of students who stayed, 26% stayed for 3 years, and 24% stayed for 21 or for 4 or more years. So the problem we had is we had the year that we ended, we had 20 high school students that were coming to the program. And it was really difficult and a challenge because we had funding for these fifth to eighth graders, and we also were always providing something new. So we really were asking for more funding to be able to keep this high school cohort, and we just weren't able to fund that, which was unfortunate. But we got really lucky to be able to get data from, this was a study that we did, but we're also able to collect data from the school district, which I nearly cried the day that they agreed to give us data, and also a data scientist to be able to look at the school data and our data for our urban scholars. But one of the things about this is a science attitude study that we gave, and what we were excited about is that we were able to keep the science scores in science interest and science engineering in the career constant from year 1 to year 4. So usually there's a big drop off in middle school. So some of the outcomes which we were interested to see, we never did anything remedial. We never did anything with school. It was always just fun science, math, computer science, anything to do with science that we thought would be really fun. But our students in the program performed at a higher rate than the students in the district. So we found in math and ELA, our scores were much higher. Now you can see the percent proficiency is still low, right? I mean, we're talking about we're like excited about 25 and over 30%, but it's still much higher than the district. So we were having an impact. This was our high school assessments, which we were really surprised about. So here we have students passing grades. So this in New York, we have standardized tests for high school topics, right? So they take these standardized tests in New York. And so this is looking at their passing rate, and they're passing with 80% or above, comparing just the district versus our Urban Scholars program. And then this figure over here just shows non-USP versus our Urban Scholars program and the kind of classes they were taking. So that was one of the effects that we were surprised to see, that our Urban Scholars kids were taking a lot more science and math classes in high school after they left our program. So we didn't even see them anymore, and they were taking these classes. This is the information about some of the science courses that they take. So starting in 2013 would be about when would see students that went through our program, right? When we started in 2009, we thought 2013 was about when we'd start to see their participation in high school. So we can see like an increase here in science and math courses over the time that they were in the program, for both math and science, for our kids, right? And then this were graduation rates. So we found for the district graduation rate was 62%, and our Urban Scholars were 93%. And then graduating with a Regents diploma, which indicates that they're college ready, we were at, the district was 13%, and we were at 43%. And one of the things we always are asked is, what is it when you were comparing these groups? They were, the data scientists matched these groups. So they were able to pick a group of students that were in the program starting in fifth grade, and they looked at the similar group of students from fourth grade. So they picked these kids and then they followed them through. So they were getting a comparative group that we weren't picking like the smart kids or anything like that. So some of the things that we felt that that really like led to our success was that it was how we responded to the needs and the desires of the students, like how we listened to their stories, and to the STEM content we provided. And we found that younger students really didn't care about the science. They enjoyed doing it, but they played with their friends, they played Minecraft, and they just liked to not be at home. That was another thing. And then older students started to think more about that this was in line with what they wanted to do and some of our STEM goals. And then, and just like I said, we wanted to make it a really happy place that's better to be being like home in your bed watching TV. So with your friends, that they're doing fun things that they felt like they were missing out if they didn't come on Saturdays. And so one of the things we learned, when you're developing a program like this, you're thinking about what you want to teach them and what you want them to learn. And sometimes you're like, wow, that was like the worst day ever and it was a bust. And then you hear them on the bus home and they'll say it was the best day ever. They loved it. And so that's really talking to the difference between our goals and their goals, right? So we can think that maybe we didn't get across what we wanted to in the science, but if they had fun and they had a good time, then we were keeping their interest in coming back and making sure they were happy. So you can't just have your STEM goals as part of the program. You need to really engage the students and figure out what they want. So we found that students prefer programs that bring novelty and variety, that they want their own placements, right? They want to be able to choose what they want to participate in. They expect to be seen and represented positively, as learners with great potential, as good people, and as individuals who want their true self to be valued. And this is something we preached at our mentors all the time, that, these kids are here and they want to be seen in a positive light, and we're here to support them and believe in them. And usually we found that when a kid is creating problems, behavioral problems, that there's a problem with the class, really, or the program, or not with the student. And so we, took that to heart and brought them out of class and switched classes if needed, put them with a friend, whatever, to make sure they were having a good experience. And then lastly, our experiences often differ from theirs, and our assumptions are not always valid for them. So just to keep that in mind, designing a program. And so after this, I think it was really interesting and, opportunistic for me, sort of, I guess. Seeing a silver lining, right? We were still running the program in COVID. I was actually on sabbatical that year, and we ran the program through. I was on sabbatical for the year, and we still ran the program through March, when we were, not allowed to run it anymore due to COVID. So during that year, I was trained as a physicist. I didn't really understand qualitative research very well, but I knew that the program had a lot a lot of what was going on in the program really needed to be explored with qualitative research. So I spent the year taking classes, reading books, and really just educating myself about qualitative research, frameworks, and methodologies. And I also created an IRB study to study the program. And unfortunately, the program ended and it was never restarted, and I wasn't able to pursue that study. But one of the good things that came out of it was that during this time, I was using a program with the kids called CoSpaces EDU, and that was a way to program using the Merge Cube and program your own activities in the Merge Cube. So most of the time, the first lesson was for students to make their home and make their people in their house and their family and their pets and their garden, and then have other students go in there and learn about them. So that was kind of the goal. And I just remember I was teaching upper level E&M, and students were struggling to understand my 3D models. I'd bring in different models and they were struggling to understand it. And I realized, wow, I could really use augmented reality to teach upper level E&M. And so I started with students here, with college students, and we started developing in Unity, making apps to understand abstract and 3D physics concepts. So it kind of I had to stop doing what I was doing in terms of research, and I spun off into the developing augmented reality apps. And just to mention, I received an NSF grant in 2022 to develop AR apps and lessons for magnetism. So I'm just going to switch into, what is augmented reality? And so augmented reality is a digital overlay on top of a camera display. And so you can see some of the figures here, the top right and the bottom left. These are examples that of our app. So you're looking at the Merge Cube. And that Merge Cube is being recognized. The pictures on it are being recognized by the camera using something called Viewphoria, something that we add into Unity. So we're able to identify the target, and then from there you can see the 3D image. And the cool thing about using a cube is that you don't lose the 3D model. So sometimes when you use a QR code or just a picture, like a playing card, you'll only have the 3D image on top of that image. But when you have a cube, you can actually rotate it and hold it almost as if you're holding that 3D abstract thing in your hand. So that cognitive recognition is kind of really interesting. And so the target is detected by the camera and the digital image or object is mapped onto the target. So in this example too, on the left, you can see the student is actually trying to use the right-hand rule by looking at the image, right, and trying to match it up and then look at the equation. And we'll talk about more at the end because I have a study that we're doing about how students are learning for example, with the right-hand rule for different concepts. So what are MARVLS? So MARVLS are augmented reality of 3D concepts that students can manipulate. So they can do that by rotating the merge cube, or they can use buttons or sliders to change things about the model. In this example here, you can see students are learning about the forces on charges. So they're able to look through their phone at the cube, and they can see in that example, there's 4 charges. So they've got like a rectangle of charge. And then they're able to modify some of the sliders and buttons on the display there, and they're able to pick their charge, and they're able to increase or decrease the value of they're able to, I think, change the distance, and also change the charge value. And so it allows us to visualize abstracts and 3D concepts. It also allows us to connect 2D representations with these 3D models, because oftentimes we show students with our handouts or in a text, a 2D representation of something that's 3D. And we often don't provide enough scaffolding for the students to really understand how the 2D relates to the 3D model. And so we're also able to visualize these 3D models that connect the variables of equations to the AR representation. So really linking an equation to what it's representing in 3D. And here I am, like I'm teaching in class, and I just took this to pictures to Staples. I took my cube, made some copies on our copier, and then blew it up, brought it to Staples, and then I made that out of cardboard. And so I'm able to show it in class, and I often like to I'll do activities in class too, but I really like anytime I'm talking about the topic, it takes me 30 seconds to show what we're talking about, to remind everybody like how we're visualizing. And this one I think is flux. Or electromagnetic induction. Yeah, so that's one other thing. So we have visual demonstrations in class, we have in-class activities, so we have lessons, and then we have some homework assignments. So connecting 2D representations to 3D models, we're able to show 2D representations either on the screen or like in the model itself. So you can see on the bottom left, we have a current carrying wire. So that's represented with like the 3 little, the line of spheres coming up out of that like kind of invisible, sort of visible, translucent wire. And then we're showing the magnetic field, the blue arrows, right, that are changing direction around the wire. And then we have this 2D representation in the model itself. And if you had the app and you were pressing on the button there will showcase the green arrow. So it actually, now we have it so that the green arrows show up in the model, but also on the sheet, on the 2D representation as well. And the same thing in the middle here with the Lorentz force, right? We're able to push on these buttons here to show which variable that connects to in the 3D model. And in this example here, we're actually able to show, if we're thinking about how is the magnetic field created in a wire due to, say, another wire, we're able to show like what the values are or what the direction is for the magnetic field above and below this wire. Show it here. We can even show how we get a changing flux, give us a current in this loop right here. And so we're able to show all that, kind of put all those pieces together, including the 2D representation. Here's an example of the right-hand rule. So we have the right-hand rule and we have the cross product. So students are able to see when they can change the vector. So they're able to turn these vectors on and off on the left. And then you'll see like this hand or this arm model that we have 2 different examples now in the app, but you can do the finger, the gesture, and we also have this arm model, and it'll showcase by pressing on these buttons, which it'll rotate the hand into a position, but it also, click on, whoa, sorry about that. It'll show both the arrow, it'll show the letter, and it'll show the fingers the way they're pointing for that example or for that variable. Linking physics equations to concepts with the right-hand rule. So we have, many applications in physics. Whenever we teach the Biot-Savart model, the students really suffer. Having the 2D representation of the Biot-Savart model is kind of tough. But we're able to show, again, with this equation, what the variables are. And we've actually since added the right-hand rule right into the model. So we're able to click on the right-hand rule and see how the hand would where the fingers would go, at this point, this location in space where we're determining the magnetic field. So as many as we see it's appropriate, we add in these equations and we add in the buttons to be able to highlight, like here, the velocity vectors is in green when we push that button. We've linked these models to like Gauss's law and Ampere's law. So like the one I found really fun to do because I really struggled as a student was Ampere's law. And in Ampere's law, you have to draw your loop. And I remember getting confused by, well, what direction is the loop in? And not really understanding that this loop is, off to the side where the current is coming through here. So I think this was a really good addition to our group with using these examples to showcase like how to think about about Ampere's law and each of the variables. So just a little bit about the MARVLS apps. We have 4 apps on the App Store. We have Physics 1, we have Physics 2, that's where all of our magnetism scenes are. We have plasma physics, which we developed in cooperation with the APS. We have one that's not there yet, but it should be up like later this week, and that's for the up and coming physics quest on quantum computing. Ours is called MARVLS AR for quantum computing, and I'll show off that a little bit. And then we also have an organic chemistry app as well for those people interested in organic chemistry and some of the organic 2 chemistry topics as well. The apps are free to download from the App Store and the Google Play Store. There's in the app, you can download a template to be able to create your own merge cube. So this is my merge cube. It's like a foam toy, and you can order it, but it's like $25. And so you can order that on Amazon or from Merge directly, but you can also use Merge's template. So they have a PDF, their template. And so I always print those on cardstock and then cut them out, fold them up, and we have our own cubes and give those out in class. Let's see, we also have lessons developed for many of our scenes. And the final thing is we're looking for collaborators that would like to use the augmented reality models and lessons in their classroom for their Physics 2 courses. So we have as part of our NSF grant, we're looking for partners. And we have lessons developed and we have some assessments. And so we could decide together what you'd like to do for that. Here's like some information, which I think, Meg, you said that people would have access to this, right? Yeah, okay. So the App Store links, so the QR codes are here. And this is just what it looks like when you open it up in the App Store or on your phone. And we have activities for magnetism concepts. So you could look in for the magnetic field. We have a lot of things within there, and the Lorentz force, we have many things in there. And then we have, the electrodynamic or electromagnetic waves, I think, are in special applications. We have induction. So a lot more things in here than just magnetism. And this is our Physics 1 app. We've updated some of the apps in here, but one of the things I think is really good is the vectors and how students understand vectors. We've been using that and it's really been helpful. We also have circular motion. So if you're teaching simple harmonic motion with a mass on a spring or a pendulum, that's great. And then some of these others are really, you could teach in 2D, but it's really nice to have the 3D, the whole kind of 3D idea about it. One of our favorites is projectiles. A lot of the students really like that. This is the plasma physics app that we developed for the APS last year. And so we have the activities or the lessons available are on the APS Physics Quest site. And you can use those. And this is our up and coming, soon to be released quantum computing app, where we have the principles of quantum mechanics. We have some introduction to bits. So kind of digital logic. And then how is that different from qubits? And we talk a little bit about spin. So some examples about spin. We talk about some of the qubit logic gates. And then we have an example for trapped ions. And soon we're going to have another example for superconducting qubits. So the lessons will be available on Physics Quest 2025. We have visualizations and lessons for the topics. And we have a walkthrough, which I can show a little bit of in just a minute. But I also wanted to bring up that we have written a paper, and we've actually written another paper that was accepted, but is not available quite yet. But we're using the mathematical sense-making framework developed by Gifford and Finkelstein. And I remember reading these papers when they first came out, and I was thinking, wow, this is a great way to evaluate how well students are learning with our augmented reality apps. And so I've kind of been thinking about it since 2019 or so when they first came out. But they provide a set of tools to understand how students make sense of physics concepts and mathematical relationships. So this is the little table that they show of how to think about the mathematical sense-making framework. And so what we have is like tools for sense-making. So you can see like up on the top part of the triangle, we have the tool, so a mathematical tool or a physical tool. And then right, like mathematical. So the top is mathematical or physical, and then the side is the object of focus. So are we thinking about like the cross product equation, or are we thinking about the Lorentz force law, right? Versus like a physical system. Like how are we thinking about let's say the Lorentz force, like how does that force act on something, right? That would be my physical object, but then my mathematical tool would be like the Lorentz equation, right? Whereas for a physical model here, we could use a physical model to understand a mathematical formalism. So in this example, like in our case, our physical model might be the right-hand rule to understand the cross product, right? And we can also use a physical model to understand a physical system. So in this case, it would be like even the physical model would be like the AR model of what you're seeing for the topic that the physical topic that you're interested in. And so what we did is we had semi-structured think aloud guided interviews where students would use the app, and we used our case study of one of the sophomores' interviews, and we included some of their quotes in the paper, in the PERC paper. So this was the example. We were looking at the Lorentz force law, and we were looking at the model itself, the AR Lorentz force model, the addition of the equation, right? And then thinking about the right-hand rule model. So thinking about that, like our basic modes for the mathematical sense-making framework is this would be the physical model. So that would be my right here, this part. And then my force on a moving charge and magnetic field, that would be like my object of interest, right? And then I'm also thinking about the Lorentz force and how does that tell us about the force on a moving charge. But in order to get here, we need to understand the right-hand rule. And so how do we understand the right-hand rule? We need to understand like how do our fingers actually provide us the information to use, or how do we use the gesture? How do we orient our hand and our fingers on our hand to use the gesture? So following like the mathematical sense-making framework that Gifford and Finkelstein developed, we like went back here to this. How do we get from here, right, to here? So how do we get from our right-hand rule to the Lorentz force to understand the topic? So we have chaining, right? So we start with our fingers to understand the gesture, and then we can now take the gesture and understand the cross product, right? And then we think about the cross product, and that helps us to understand the Lorentz force. And so this following along, this is our physical model is the actual scene for the right-hand rule that helps us understand the right-hand rule gesture. And then here we put that one in here, and we now have the gesture to understand this mathematical concept, right, of the cross product. And then we now have the mathematical idea of the cross product that's helping us understand the mathematical model of the Lorentz, or the mathematical object that is our Lorentz equation. And so we can put it all together, right? So we have like this transition from the model to this new Lorentz force. So these are different ways to understand the force on a moving charge. And then in order to go from the Lorentz force equation, we need to understand the right-hand rule and how that relates to the cross product and how that relates to the Lorentz equation. And so then putting it all together, we have the first one, the AR model. So that's on the top. And then kind of the steps we need to take to go from the right-hand rule to the cross product to the Lorentz force to understand the force on a moving charge. So that's kind of how we're using the mathematical sense-making framework to understand how students are learning. This was based on how the student was going through the process to understand that AR model. And so these are some of my references. The first few are about the Urban Scholars Program. So the first one, I think, through the third one. And then after that, the fourth one through 8 was having to do with our paper and for the PERC conference. And we had, and then a couple here from Gifford and Finkelstein. So this is, I also wanted to show you, do we have time for me to show the video, or should I stop?
Yeah, you've got time.
Okay. So if you'd like to participate in the study, you definitely contact me. Would love to have people to work with. But I just wanted to show you the app because I think it helps to like understand it a little bit. And this is on the APS website. I just want to go back. I have my time here, so 3:57. I'll just show you. This is like what the app looks like when you first pull it up. And then let's see if I go to 57. Here we go. This is an example of, I can play it too.
One, and we can create a superposition. So you can see the block sphere vector is moving all around. It gives us percentages of the probability of it being in the 0 or the 1 state. And then we measure and we can see the state collapses into the 1 state. We can go again, superposition.
Okay, and now I'm just going to go to 5:14.
Or add a bit, add a second bit, and add a third bit, right? We see that the input is 3 bits, our calculation is 3 bits, and our output is 3 bits. But now if we change the type, we'll go back to just 1 bit, and we look at qubits, we can see that if we have on the left on the input, if we have 1 qubit, right, then we know that we can have 2 states here, right? And so our calculation doubles, our number of calculations that we can do doubles, and our output still collapses into just 1 value. We can look at these and see like what they look like in 3D. We can now add another bit, right? And this we see again, our input is in a superposition of states, which means that there can be any combo of 0 and 1 for each bit. So we get, see, 4 calculations that can occur, right? Whereas when there was just bits, it was just still, again, 1 calculation, and our output collapses to just the value of each of the 2 bits. And then if we add another one, we see that we get up to, for 3 bits, we have 8 calculations that can happen at once. And so this is just to illustrate how quantum computing is pretty powerful, because the number of qubits increases our number of calculations exponent.
Okay, and then I wanted to show you one more. Okay. So this is just an example of like some of the lessons that we have. So just lessons that go along with each of the models. And then I'll just show you this one. This is one of my fun ones, I think.
Its lowest energy state, the down state. There's some here about how to play in case they weren't sure. So just right in the game, they can read about that. It has a scroll bar so they can move around. We can close this, and then we can open up the buttons. So what this allows us to do is turn on the laser. So you can say the laser's on. We're going to choose the down to up transition. And so you can see we went to a higher energy color. And when the frequency gets close to the right frequency, you can see to indicate that the electron will turn that color, just to let students know I don't know if this is going to let me use the pointer too, but you can see it just went from down to up. But let's just do that again. Let's just reset. I think we might have to see. Yeah. Okay, there we go. So it's down, and now we're going to drag this over. When we get close, it should turn purple, like the color of the laser. And now you can see it goes from, that's in the down state, and now it's going to go into the up state. There we go. We can switch and try out a lower energy. So this is the up to down state, and you can see we're in the up state. We're getting close. We're getting red to match, and we're in the up state, and then we just went to the down state. And then for superposition, where we need to find where the right energy is. And so we can see, oh, it's starting to turn purple, so we must be close. And then you'll notice on the screen that this pulse button shows up. So right here, this pulse button, you can see right here, and that allows us to actually pulse the laser. Right, so when we pulse the laser, it rotates that electron into a superposition of 0 and 1, right? So we can pulse again.
Okay, so I think that's enough just to showcase what the quantum computing app is all about. And okay, so I think that's all I've got. If anybody has any questions, I'm happy to answer them.